Hello viewers, welcome to the lecture series on CAN protocol. In this video, we are going to see CAN error types and how it is handled. So let's get started. There are basically 5 types of errors in CAN protocol. The first one is called bit error, next is called stuffing error, third is called CRC error, fourth is called acknowledgement error, fifth is called form error. So coming to the bit error, it is basically happens whenever transmitted and received bits are different. Say a transmitter transmits a dominant bit, but receiver receives a recessive bit, or vice versa. Exceptions are in arbitration, acknowledgement, and passive errors. Bit stuffing error basically occurs when more than 5 bits of equal polarity inside a frames are detected, either dominant or recessive. CRC error receives CRC code that doesn't match with the calculated code. Say transmitter sends a frame with a particular CRC. After reception by the receiver, when it calculates, it will be different. In such case, CRC error will occur. Acknowledgement error. This occurs when transmitting node receives no dominant acknowledgement bit. That is, no receiver accepts the transmitted messages. For CAN, it requires at least a single node needed to be acknowledged the transmitted frame. Form error. It's basically a fixed form bit field contains one or more illegal bits. Say example, violation in the end of the frame format, or CRC format, or acknowledgement delimiter formats. If a single bit error also occurs in these fields, it will be called as form error. So coming to the bit error, as I explained in the previous slide, it occurs if the transmitter sends a dominant bit but detects a recessive bit on the bus line, or transmitter sends a recessive bits but detects a dominant bit on the bus line. An error frame is generated and the message is again retransmitted or repeated. When a dominant bit is detected instead of a recessive bit, no error occurs during the arbitration field, as I told, exceptions or acknowledgement slots, because these fields must be able to overwritten by the dominant bit in order to achieve the arbitration and acknowledgement field. Coming to the bit stuffing error, if 6 consecutive bits with same polarity are detected between the start of the frame and the CRC delimiter, the bit stuffing rules has been violated. A stuff error occurs and an error frame is generated in this case, and again the message is retransmitted. CRC error. This basically CRC sequence is transmitted in the CRC field of the CAN frame. The receiving node also calculates the CRC sequence using the same formula that has been used by the transmitter and performs a comparison to the received sequences. If the node B detects a mismatch between the calculated and the received CRC sequence, then CRC error has been occurred. In such case, the node B in this example will discard the message and transmits an error frame to request a retransmission of the erroneous frame or garbled frame. Say acknowledgement error. Say here a node is transmitted data, and at least one node must send an acknowledgement. But see, on the canvas the data is sent, but there is no acknowledgement. In such cases, acknowledgement error has occurred and message has to be repeated. No frames are generated though. Form error. If a transmitter detects a dominant bit in one of the 4 segments, that is CRC delimiter or acknowledgement delimiter, or end of the frame, that is 7 recessive bits, or interframe space. In all the above cases, a frame error has been occurred if it is violated, and the error frames are generated in this case, and again the message will be retransmitted or repeated. Next, how the CAN handles the error. Basically, it has an error management unit. What error management unit's function is to cancel erroneous messages at all CAN node. Next, disconnect the erroneous nodes from the CAN bus if they detect too many errors. If they generate many errors, say if a node generates multiple errors, it will be disconnected from the CAN bus. Next, error management uses two error counters. As I explained in my previous videos, the first error counter is called receive error counter. Second is a transmit error counter. CAN controller may work in three different states. That is, a CAN node has three different states: error active state, error passive state, bus off state. Error active state, for each detected error there is generation of an error frame. So whenever the node is in error active state, for each detected error there is generating an active error flag. Basically it is 6 consecutive dominant bits. In the case of error passive state, for each detected error there is a generated and passive error frame or flag. Basically it is a 6 consecutive recessive. If a node is active error in state, it will be 6 consecutive dominant bits. If the node is in error passive state, it must be have 6 consecutive recessive bits. Bus off state. If too many errors are detected by a single node, then this node is automatically disconnected from the bus and it is called as bus off state. So status of the CAN node. CAN node status level are switched depending on the value of TEC and REC. See, basically TEC or REC are counter which may be increasing or decreasing based on the current value of these TEC and REC. The node can either be in active error state, passive error state, or bus off state. Basically, a node is in error active state if transmit error code and receive error code is less than or equal to 127. In such case, it will generate 6 dominant bits. If a node is in error passive state, it means that TEC or, here you need to observe guys, in the error active it is and, in error passive it is or. TEC and REC must be in the range of 127 to 255. Then it will generate 6 recessive bits. If a node is generating too many error frames, that is the TEC count is greater than 255, in that case the node will be in bus off state. It is basically disconnected from the CAN network. This slide basically shows you the state transition diagram of an node based on the error state they are in. They can be either in error active, error passive, or bus off state. A node will be in error active state whenever TEC and REC counters are less than 127. So if either of the counter crosses 127, it will be moved into error passive state. Say if a node is transmitting too many error frames, in such case TEC crosses 255. In such case it will be goes into bus off state. Once the CAN controller resets the node, it will move from bus off state to error active state. So these steps that CAN uses during error for error handling is demonstrated in this slide. For each CAN node which detects error, which can be either global or a local error, sends an error flag to inform the other status about their error. An error flag is basically queue of 6 consecutive bit, either dominant for error active node and recessive 6 recessive bits for error passive node. So in case of a node detecting a local error, it will send an error flag. The other nodes detects an error because of this flag and they also sends their error. Say after, like in this way, after receiving and sending an error flag, all the nodes cancel the message. Each node which detects an error increments his error counters. Transmitter of the cancelled message will be retransmitted automatically this message. Basically, once this error is detected, the transmitting node will retransmit the frame. Next, coming to the error counter, as I explained, this slide basically demonstrates how the counters are incremented and decremented for every successful transmission. That is, after reception and transmission of the acknowledgement, the TEC or REC counters are decremented. If any error occurs, in case of TEC it will be incremented by 8. In case of REC, either it is incremented by 8 or by 1 based on the different types of error detection. Say bus off state, a little bit detailed expression we shall see. A unit is in bus off state when, so as I told, when it is generating too many error frames, that is its transmit error counter is greater than 255. Here the receive error counter is not considered at all. So whenever a node is in bus off state, it is practically disconnected from the bus and cannot either receive or transmit anymore. A node can only leave the bus off mode via hardware reset or software reset and subsequent initialization carried out through the host. So in case of BOS specification, TEC and REC are set to 0 and unit must receive 128 times a field of 11 consecutive recessive bits in order to move from bus off state to active error state. The next slide is about warning levels. Say a warning level for each of the node is set whenever TEC counter is greater than 96 and or a receiving error counter is greater than 96. So when a unit reaches a warning level, it is indicated to the main controller CPU that the unit is heavily disturbed and an error warning flag is set. Optionally, an interrupt might also be result from this. The error warning flag can be cleared whenever TEC is less than 96 and REC is less than 96. See why we use or what are the practical use of warning levels means, by constantly checking for error warning flags, it can be determined whether the units get near to the threshold of error passive state. That is whether either TEC or REC is above 127. Unfortunately, by checking this flag, we cannot determine whether it is still in error active state or in error passive state. So this diagram depicts all the states of the node. If the counter is less than 127, the node is in error active state. If it crosses 96, error warning flag is set and then indicated to the controller CPU. If it crosses 127, the node will be in error passive state. If it crosses the TEC value is greater than 255, it will be in bus off state. So in this case, based on REC counter, we don't consider for bus off state, but we consider REC value for error passive state and error active state, also for warning. Say the probability of not discovering an error is about 4.7 into 10 raised to minus 11th of a time. Say example, a CAN bus is used 365 days per year, that is all day, that is 8 hours per day, with a transmission speed of 500 kilobits per second, and error arises every 0.7 second, means in 1000 years only one error remains undiscovered in the CAN network. In the example 2, if you consider a CAN bus in a car is running at 500 kilobytes per second with an average bus load of 15%. The average size of a frame is CAN frame is 110 bits for an average operating time of 4000 hours. Only one error in every 100,000 errors automobile remains undetected. So I hope this was useful. Thank you. Keep subscribing. Have a nice day.